Good evening, everybody. Tonight we're going to be looking at graphing exponential functions by hand. So just a couple of things before we get started. I just want to remind you on a couple of items. First of all, if our parent function is always written as b to the x power. B is just some number, and b is referenced as our base. Now we've got two things here. If b is more than 1, that causes what we call growth. If b is in between 0 and 1, that's going to cause decay. We always have a y-intercept of 0, 1, and we always have a horizontal asymptote of y equals 0. Now, there's a couple of transformations that we can apply here. The first transformation that we can apply is multiplying our base by some number. And what that does is we typically reference that value as a, and that would cause what's called a vertical stretch if a is more than 1. Or it would cause a vertical shrink if a is in between 0 and 1. And the second thing here is if a is negative, it would cause a reflection over the x-axis. So if I said a equals negative 3 here, that would be a combo problem. First of all, it would be a vertical stretch. A is more than 1, just the number. 3 is more than 1. The second thing is the negative. The negative causes the reflection over the x-axis. The second thing we have here is if we actually add or subtract something from our exponent, from x while it's being the exponent. And this will cause a horizontal shift, either left or right. If we see a minus c, it's going to move the whole function to the right c amount of units. If we see a plus c, it's going to move the entire function left c amount of units. Now, the last thing that we can do is we can either add or subtract a value here at the very end, or we could even add or subtract it at the beginning. And what this would cause is a vertical shift. D is going to move the whole thing up, minus D is going to move the whole thing down. And I do want to just make this note, this does include your asymptote. Now, what I'm going to be looking at doing is just graphing a couple, oh, excuse me. I'm going to be looking at just starting by doing a couple of vertical stretch and shrinks, and then doing a horizontal shift combined with a vertical shift, and then combining all three different types of transformations together. So I hope this helps you out, and if you have any further questions, please let me know. Okay, so first thing I'm going to start doing is I'm going to start by graphing f of x is equal to 3 to the x power. The first thing that I would do in this case is I would graph my horizontal asymptote. I know my horizontal asymptote of the basic parent function is y equals 0. And I also know my parent function for 3 to the x would have a y-intercept of 0, 1. Now from there, I know that my base here is 3, which means I'm going to multiply my consecutive y values by 3 each time to generate the next one. So when x is 1, I would have a y value of 3. When x is 2, I would multiply 3 by 3 again, which would give me 9. I would do it again, and I would end up with 327, which is going to put me way off the charts here. And then I would have 481, so on and so forth, 4243. And then on the left side, I just need to get this closer and closer to my asymptote. I know this function is increasing because if I look at my consecutive y values, I go 1, 3, 9, 27, 81. Those y values are getting very large, very fast. So my growth function is always increasing. Now for my second function, what does a change of 2 times 3 to the x do? First of all, this would be a vertical shift of 2, and really all this is going to do is it's going to change my starting point. I started off at 0, 1 originally, but what this is going to do is cause me to start off at 0, 2 instead. Now, once I have this, I'm still going to follow the same pattern still going to multiply my y values by 3 to get to consecutive ones. So I would start off by going 2 times 3 would give me 6. And so I would have the coordinate 1 comma 6 in my secondary function. I would multiply 6 by 3 again, which would give me 18. Now, I know that's going to put me a little bit off the chart, but that's going to give me these points right here. And so I can see that's the side that's moving away from the asymptote, which means that this side has to get next to the asymptote. Now, why is this called a vertical stretch or shrink? This is called a stretch because if you look at corresponding y values, 18 and 9, the 9 was multiplied by 2 to get 18. 3 was multiplied by 2 to get us 6. 1 was multiplied by 2 and gave us 2. This is going to increase all of our y values by a scale factor of 2. Okay, let's take a look at another one. This one we have two transformations. The first is we're going to have a vertical stretch of 4, and the second is we're going to have a reflection over the x-axis. Just like on the last problem, I'm going to start by sketching my horizontal asymptote in purple up here. So since I'm not moving up or down any, I'm still going to leave my horizontal asymptote at y equals 0 with a dotted line. Now, just like on the last problem, I'm going to sketch this by just kind of assuming that -4 is my y-intercept. So at 0, -4 would be my first coordinate. At that point, I'd want to multiply my y value by -1/2. So -4 times 1/2 would give me -2, which would tell me my next coordinate would be -1, -2. I would then continue the pattern, have -2, -1, and then I would have that should be, what's wrong with me tonight? We've got +2, -1, +1, -2. We would have +3, -1/2, and so on and so forth. So we can see that this is my side getting closer to my asymptote. Now, if we multiply to go forwards, we would have to divide our y values to go backwards. So how do I divide by a fraction? -4 divided by 1/2. I take my denominator, I flip it and multiply. So -4 times 2 over 1 would give me -8. So at -1, I'll have a y value of -8, which would give me my final coordinate. And just kind of be able to connect the dots and go from there. Okay, so let's look at one that actually has some transformations here, left and right, up and down. So I can already go ahead and see I'm going to move down 3, and I'm going to move left 4, based on what we had said earlier. So from this coordinate right here, I'm going to move left 4. So I'm going to go 1, 2, 3, 4. Then I'm going to go down 3. 1, 2, 3. Now here's the weird thing about these transformations. The graph thinks that this is the origin. The graph thinks that this coordinate is 0, 0. Due to the little trick that we've kind of played on it. So our horizontal asymptote is going to go through this point, which would be at y equals -3. The next thing that we're going to see, so from this new origin, I'm going to graph my just regular parent function 3 to the x power. So from the origin, we know that the normal point is 0, 1. So from this point, I would graph just kind of like quote-unquote 0, 1. I know that point is not really 0, 1. It's just kind of a method for me to be able to sketch this quickly by hand. And so since my base is 3, that tells me I need to multiply my y value by 3 to get further and further y values. So 0, 1, I would then have 1 and then 3. I would have 2, 2, 9, and this is all again in reference to that new quote-unquote origin. And then I could just kind of have this going back this way. Now here's the thing, I know that these points are not really 2, 9, 0, 1, and 1, 3. So here's the thing, I would have to actually remove these once I'm done with drawing my sketch, and just kind of use those as a frame for actually drawing the sketch. But overall, this would be my finished product here. Alright, let's look at one where everything gets put together. The first thing I'm going to do is I'm actually going to move my origin. So I can go ahead and tell this is going to go up 8, that's going to go left 2. So here's the thing, my graph thinks that this nice little purple point is the new origin. It thinks that that point is 0, 0. We all know that's not really the origin, but that's just kind of what we use to help sketch the picture. Now we know that we're going to have our dotted line, our horizontal asymptote going side to side, straight through the origin. In this case, it's really at y equals 8. Now from this point, we know that our y-intercept would be at -4. So I'm just going to go ahead and pretend that this point is 0, 0. From this point I would need to go down 1, 2, 3, 4 units. And the function thinks that this point, this big red point right here, is 0, -4. So just like earlier, I would multiply my y values by -1/2. So I would have 1, -2. I would have 2, -1. I would have 3, 1/2. I would connect the dots and go out that way. I would have -1, -8. I could see my graph going out this way. This time let's actually assign a couple of real ordered pairs to this function. So I see that I've got the coordinate -3, 0. I've got -2, -2, 4. I've got -1, 6. I have 0, 7. And I have 1, 7.5. Okay. So let's look at one last example. Okay, so this time I have 3 times 2 to x minus 2 power followed by -6. So first thing I would do is I'm going to find out where my origin is. This is going to tell me I'm going down 6, and I'm going to go right 2 this time. So my graph has been fooled into thinking that this point is 0, 0. I know that would be my y-intercept of 0, 3. So from this point I would have 1, 2, 3 would be my actual coordinate that I'm going to use to graph. I've got my horizontal asymptote. And then I'm going to take my y values, I'm going to multiply them by 2. So 3 times 2 would give me 6. 6 times 2 would give me 12. And then so on and so forth. I would connect my dots, going up and to the right, and then I would also go down. On this case, I can see that 3 divided by 2 would give me 1.5, so I can just kind of sketch it a little bit better. That gives me a loose sketch. At this point, I could go through and find some of these ordered pairs that I plotted, but I'm not going to worry too much about this one. The trick was to find an accurate representation of what the graph should look like. If you have any further questions, please let me know.